So let's see. I hope you saw the assignment that trying to get a little bit of traction, or a little bit behind, but a little bit catch up in lectures. The final project, I'll be distributing that a little bit later. I will discuss it on next Wednesday, and we have a month to do it. Right. Okay, so let's see. What we were talking about the last lecture was the interaction of quantized fields and atoms. Okay, so as we will see, as we will develop in this lecture, we take what is a fairly complicated and sophisticated problem of quantum electrodynamics, which is hard to solve, and baffling in many ways. There's all kinds of infinities and craziness. And we'll distill it down, as is our wont in quantum optics, to a very simple model that we can solve. But interestingly and importantly, we don't just do it because we can solve it. We do it because it actually has import in the physical real world. Okay. So we started the discussion. We said, well, we could write down what's called the minimal coupling Hamiltonian that couples the fields and the charges through the vector potential and the scalar potential. In the Coulomb gauge, as we've discussed, only quantize the transverse part of the vector potential. And if we make a multipole expansion, under the assumption that all the charges are moving non-relativistically, and the extent of the charge distribution thus is small compared to the time it takes light to transfer across that ensemble, that's equivalent to being able to make a multipole expansion in electrodynamics. Then we can take the dominant term for our atom, which is the electric dipole term. That's the most important coupling term for neutral charge distribution. And that couples to the electric field, okay, at the center of mass position of the charge distribution. This is then the Hamiltonian that represents the, I guess I left out one important thing, which is the Hamiltonian of the field, excuse me. So there's the Hamiltonian of the field, and then this is the Hamiltonian of the atom, and then the interaction term between the atom and the field is expressed here, dominated by the electric dipole. Okay. And we further simplify by restricting our attention to a two-level atom. When we can do this, we have to think about that a little bit more carefully. What we did in the context of when we looked at classical laser field interaction, we were saying the laser was tuned near to this resonance. There ain't no laser. We're just talking right now about the overall field. So we have to think about when it makes sense to restrict our attention to just this two-level system. Come back to that in a moment. But we're just going to do that for now and justify it later. Okay? Right. Okay. I don't know if I mentioned this, but I just wanted to mention one small detail here, which is that when we quantized the field, we did it in terms of the vector potential, right? We wrote down the modes of the vector potential, and then wrote down a quantum vector potential, and then from that derive the electric and magnetic radiation fields. And then there was an I out in front here because it was the derivative with respect to time, right? That's kind of traditional from a quantum electrodynamics point of view, but it's a kind of irrelevant point for us. There's no reason to talk about the modes of the vector potential. We can choose any complete set of modes we like, and since at the end of the day we're working the electric dipole approximation, and it's the electric field we care about, not the vector potential, then you just drag around an extra I for no reason. So you might as well just write this in terms of the modes of the, absorb that I, and these are now the modes of the electric field rather than the modes of the vector potential. And that's the convention I prefer. All right? Good. So with that said, we have now the Hamiltonian of the atom plus the Hamiltonian of the field plus the interaction Hamiltonian. And the Hamiltonian of the atom, it's just my two-level atom. So I just have these written in terms of those energy eigenstates, or if I like, I can write it in terms of my pseudospin where spin up is the excited state and spin down is the ground state. And the Hamiltonian of the field, which I hadn't written down before, is the harmonic oscillators of all the modes. And as we say, we ignore the 0 point because it plays no role in any of the dynamics, and it's some funny big number which we don't need to drag around. Okay? And then we have the interaction term, which was minus d dot E, and if we plug in our electric field over here, then this is equal to sum over the modes, h bar, something we call G, AK plus h bar star a dagger sigma plus sigma minus, where we define this coupling constant, it's a frequency G, as the electric field dotted in, so it's DEG dotted into the electric field of the single photon. Well, it's actually a factor of 2 off, but okay. So what is this? Well, this is like the single photon Rabi frequency. Right? D dot E, if this were the electric field, we would say this is the Rabi frequency, right? H bar capital omega is the dipole matrix element times the electric field strength, right? But this is the electric field strength of a photon in the mode. So this is, now there are factors of 2 that are, you know, one has to be careful about. I just make a little aside over here, and let me just put it over here for a moment, just to remind you of one small factoid that if you want to keep track of all the factors properly. Classically, we define the Rabi frequency of minus E dot E of the laser, right? And the electric field strength of the laser, we wrote, is, let me call this E0. So we wrote E0 of the laser. If I wrote the electric field of the laser at some position as a function of time was the real part of some amplitude e to the minus the laser t, right? Now the real part of this is equal to this plus its complex conjugate. And if I take this to be linearly polarized, then I'll just take that to be real. Right? I could make a star here if I wanted to. Over 2. Right? That's the real part. You take that plus its complex conjugate over 2. And so there's this factor of 2 over here that we have that's careful compared to if I write the electric field as its positive frequency part plus its negative frequency part. Let me call this the complex amplitude. Then you see that the positive frequency part is half of the complex amplitude. Right? Because this is, it's over 2 is the positive frequency part, and that over 2 is the negative frequency part. Okay? So really, this is not the Bakker-Rabi frequency, but half of it. Half of the single photon Rabi frequency. Okay? So a little aside, I'll come back, you'll see in a moment where those factors of 2 arise. Okay, so with that said, what we did, we say, all right, if I look at the interaction Hamiltonian in the interaction picture, which means going to the frame that is rotating with the free field and the free evolution of the atom, then this interaction Hamiltonian has the following form. So that's going to the interaction picture and then multiplying out these 4 terms. Okay? Where delta is the difference between that frequency and the resonance frequency. Frequency of the photon minus the resonance frequency of the atom. Okay? So, as we discussed last time, these terms are the anti-resonant terms, and these are the terms that can contribute to resonant phenomena when the frequency of the photon is at or near to the resonance frequency of our 2-level atom. Okay? And we call these things from what we did when we thought about this with the classical field, these are the co-rotating terms, and these are the counter-rotating terms. So, importantly, when the modes of interest the detuning and this coupling constant are much, much smaller than the resonance frequency, then we can neglect the counter-rotating terms. In dynamics. Now, to see that more rigorously, what one would have to do, in the same way that one would write down either Heisenberg equations of motion or equations of motion of the state in the Schrödinger picture with time-dependent coefficients, we would see ordinary differential equations with time-dependent coefficients with big time dependence and very slow time dependence. And then one has to use the theory of solving ODEs to show how those rapidly varying terms do very, very little to the solution, and we can neglect them. And that, of course, is the rotating wave approximation. So, we are, with that said, we have going back to the Schrödinger picture, the rotating wave approximation involves only the resonant terms. That is, I raise the atom with an absorption of a photon, or I lower the atom with the emission of a photon. This guy should have had a dagger. No one noticed. Or maybe you didn't see it. Right? And so this is the interaction Hamiltonian in the electric dipole approximation and the rotating wave approximation. And that is our fundamental Hamiltonian that we always analyze in thinking about a two-level atom interacting with the quantized electromagnetic field. We've made a number of approximations, but approximations are good. You make them when you can. You don't avoid doing approximate calculations. You do approximate calculations if the approximation is good. And this is damn good for quantum optics. So we have our interaction term now in the rotating wave approximation, and we have the field. Okay. Very good. Right. Okay, with that said, now we're going to be even more radical. Okay? This is the right Hamiltonian for thinking about an atom in free space, in the vacuum, where it can talk to all the modes of the electromagnetic field kind of equally, depending upon how close their frequency is to resonance. Okay? But we're going to now talk about cavity quantum electrodynamics. So, or what is known as cavity QED. In cavity QED, we think about, maybe what I'll do is begin this discussion with a little bit of AV fun. Let's see if we can make this work. First, I have to turn the computer on. So, should we turn off the light? Does it matter? Can you see it okay? Better to turn off the light. Right. So, here is an example taken from some graphics from Serge Roche's website. Serge Roche was one of the recipients of the Nobel Prize in 2012 for the manipulation of individual quanta. Some of the real seminal experiments that were done, mostly in the 1990s. And what you see here is in this particular case, this is a microwave, a cavity that stores microwaves at about 50 gigahertz. They're superconducting, they're extremely highly reflecting mirrors, so the photons don't get absorbed, and you need metals for microwaves to make microwave cavities, so you have to make these extremely good, and most of it was polishing these things and making them super duper uber good cavity. Okay, and an atom, in this case, is a thermal beam of atoms, flies through the cavity, and this donut is meant to represent atoms in circular Rydberg states. Okay, so you may remember, if you ever learned it, that in quantum mechanics, when you think about the orbits of electrons around the nucleus, and you quantize that, you have a principal quantum number, and then you have the orbital quantum number, right? The orbital quantum number, what can it be? Just from, if you have an n, what are the possible values of L?
Minus n plus n.
This is the magnitude of the angular momentum. It's a positive number. L goes from 1 to what? 0 to n minus 1. Good. Refresher. So the states with the maximum L are like the analogs of circular orbits when you think about a given energy, right? So if n equals 51, that's going to Rydberg, and L is 50, that's a circular Rydberg state. That state has an extremely long lifetime, right? And so that's why they did it. Compared to if you're not and making it is hard. It's hard as hell to make such a state. Just as an aside for those of you who don't know, why don't we do that in my lab? You're not going to get it. You're not going to do that. And they couple that, they call it E, and they couple it to G, which is 1L down. L equals 49. Okay? Those two states are separated up there in high in Rydberg land by 50 gigahertz. So this is not an optical transition, it's a microwave transition. And this cavity, there is a mode of the cavity that's exactly resonant, or can be tuned to darn close to that resonance, okay? So in that situation, you can think about the next energy level, the next mode of the cavity is so far from resonance from that you can ignore it. And you can think about the whole electromagnetic field as one mode. It's a single mode of the electromagnetic field, which is in the harmonic oscillator that interacts with this two-level system. And making nature, nature doesn't provide that kind of simplicity, but we can engineer nature to be able to explore that kind of very, very pure and clean model. This kind of physics, I come from this tradition, was roundly criticized as like, what? This is a baby model of one mode of the field coupled to so, grandma could diagonalize that. Grandma was smart, but come on, what the heck are we? But this kind of physics, it ultimately was recognized as so important because it gave us this kind of toy physics model, as we like to call it, serves two purposes. One is it helps focus the mind on the essential things that are going on by not making the model so complicated. Sometimes nature's too complicated for us to understand. We want to distill it down to the spherical cow for a reason. But sometimes it's also interesting in the sense that it becomes a platform of kind of applied engineering. this kind of system is now at the heart of what you may have heard of Google's quantum supremacy experiment. It is this physics. Instead of an atom, we'll talk about this in a moment, what they actually have is what's called circuit QED. I'll skip down to that. So in circuit QED, your two-level atom now represents two levels of a superconducting circuit, which is anharmonic, which has two energy levels, which represent, in the Josephson junction, an artificial atom. And the mode now is a microwave transmission line. This was developed by folks out at Yale. Fundamental work. Steve Gervin, who many of you have met, is one of our secret advisory council members, was the brainchild behind Circuit QED. And now we'll talk a little bit more about that in a moment. But this kind of physics is at the heart of modern quantum computers, all based on this idea of a two-level system coupled to a single mode of the Hamiltonian field. You know, those superconducting cavities are hard in themselves. If you want to do things at room temperature, you can do that, which much better mirrors at optical frequencies with dielectric coated mirrors that can be extremely good cavities. But we'll see some of the trade-offs between the optical version of cavity QED and the microwave version. We'll come back to that in a little bit. Okay, so we'll come back to our AD in a moment. Look at that fancy stuff. Right. So what we're going to talk about today is what's known as the Genies Coming model. James and Cummings wrote this down in 1963, even before I was born. As an interesting idea in thinking about the differences in full electrodynamics to a toy model. They weren't really thinking about this in the context at that time of actually making such a thing. It was an exploration of thought. And the model is a single mode of the electromagnetic field coupled to a two-level atom in the rotating wave approximation. Okay. So with what we have there, now we have one mode of the field. That mode is like that, for example, that microwave mode. It has some particular frequency. It has some particular polarization. Okay. So the cavity, the field now is reduced to just a single harmonic oscillator. We don't have to label the mode, it's just one mode. And this is the cavity frequency. Okay. So that's the Hamiltonian field. We can have a 0 point, but we don't need to bother with it. We have the Hamiltonian of the atom. It's up there, I'll just write it again. I'm going to take the ground state energy to be 0. I can set it to be anything I like. Okay. And then we have the Hamiltonian of the interaction in the rotating wave approximation. And it is this. I absorb a photon, raise the atom for our emit a photon, lower the atom, where this G is real. In a cavity, we have a standing wave, and so we can take the mode amplitude to be a real amplitude. Yeah, David?
Is there any advantage to using second quantized operators to represent the electrons, the fermions?
They are here. This is the quantized matter. But in this case, we have distilled out all of the details. I mean, I could have a ytterbium atom, which is some God knows, rare earth element with an F shell, something or other. But at the end of the day, I could care less about all the details of the many electron physics of that. There's just some energy levels of that system. And there are two of them that I've chosen such that their splitting is close, darn close, to some frequency in the cavity. So the many-body physics of the electrons is buried in this whole abstraction of E and G, the end. All right, moving on. All right, so let's clean that up just a little bit, because this is so beautiful. By the way, this is an example of what is sometimes known in condensed matter physics as a spin boson model. It's a particular example. We'll talk, and maybe if I have a moment after, I'll talk about more general. You can think about this as a spin, not a bose, but a boson, not a boso. In that I have a two-level system, which I can think about as a spin 1/2 particle, interacting with a harmonic oscillator, which is a boson in a second quantized sense. So people call this a spin boson model. It was studied by Caldera and Leggett, for example, in the 80s as an example. The condensed matter physicists ignored the quantum optics until they decided it wasn't. They didn't actually pay attention. They did it themselves. But what's different about this typically is this important point, which allows us to solve things and is a good approximation, a rotating wave approximation. All right, now there's a very important situation which happens when we have this rotating wave approximation, is that there's a new symmetry that has been introduced into the system that wasn't present before we made the rotated wave approximation. And that symmetry is related to a conservation law. What is that conservation law? Well, let me define NT as the number of photons plus the number of atoms that are in the excited state. Okay, which if I like, I can also write for symmetry as that. Like that. Okay. It's easy to show, and I ask you to do it yourself, that if I look at the total Hamiltonian, this commutes with the total with NT. You just have to do that commutator yourself. So, what this says is that NT is conserved. There are eigenstates of the Hamiltonian which are also eigenstates of the NT. And there exists a basis of eigenstates of the Hamiltonian for which NT is a good quantum number, because NT commutes with H. Okay? What does NT physically represent? Yeah?
Like number of particles.
Something like that. It's the number of excitations. This is the total number of excitations. So if I have, say, for example, n photons and the atom in the excited state, well, I could also, or I could have n minus 1 photons, or n plus 1 photons in the atoms in the ground state, right? And that's all I can have. So what I need to say by that is the following. Let us look at the Hilbert space that describes our spin boson model. The total Hilbert space is the Hilbert space of my two-level system tensored into the infinite dimensional Hilbert space associated with that. Yeah, Andrew.
The number operator for this, the qubit should be just sigma plus.
Oh yeah, without the dagger on it. Yes. Sorry. Excuse me. Yeah. The dagger's already there. Thanks. Sigma minus dagger. Right. So what I was saying is the Hilbert space is the Hilbert space of the two-level system, and the infinite dimensional L2 norm square normalized functions on the line, right? So a basis for that Hilbert space is the tensor product of, say, the basis of the atom and the Fock states. That's a good basis, right? So we typically write that like this, where this, of course, is just a product state, atom in the ground state, and photons in the cavity in the mode, or atom in the excited state, and then photons in the cavity. Now, the fact that NT is a good quantum number means that I can block diagonalize the Hamiltonian for fixed NT. So, what are the basis states that we would write down? So if I have NT is 0, there's only one state that has 0 excitations. That's the field in the vacuum and the atom in the ground state. That's 0 excitation. I have 1 excitation. Well, that could be 1 photon in the cavity, atom in the ground state, or atom in the excited state and no photons in the cavity. That has 1 total excitation. That excitation might be in the atom or in the field. Okay? I could have NT equals 2. That might be the atom in the ground state with 2 photons, or the atom in the excited state with 1 photon, etc. So by grouping the basis states in this way, we know that the Hamiltonian has no off-diagonal elements between the different blocks, because NT is a good quantum number. Is that clear? So if I were to write a matrix representation of my total Hamiltonian, it would, have a 1 by 1, a 2 by 2, a 2 by 2, etc. With zeros everywhere. This would be I'll call this A0, H1, H2, H3, where this guy has nt equals 0, nt equals 1, nt equals 2, etc. Okay? And so in order to find the energy eigenvectors and eigenvalues of the joint atom quantized field system, all I need do now is diagonalize a 2x2 matrix. Well, I have to diagonalize a whole series of them, but I can do it generally for an arbitrary n. And we know how to diagonalize a 2x2 matrix. It's about the only thing I know how to do. All right? So we just have to be able to express the Hamiltonian for our two-level systems, now representing these different blocks. All right, so let's do that. We have our Hamiltonian. What we need to do is, so we seek the basis representation, or the matrix representation, I should say, of Hn. For n, I'll call it n sub t, so that I don't confuse it with the number of photons. Okay. All right. So let's say n sub t is equal to n. The basis is Gn En minus 1. Those are the two states which have a total excitation number n, right? So now we have to find the matrix. So let's look at the diagonal matrix elements first. What is the diagonal matrix element here? Remember, let's come back over here. Probably maybe easier. Here's our Hamiltonian. And that's our interaction.
The sigma z part.
Right. So we have to think about the matrix elements here. So firstly, we have the field term, right? So what does the field contribute? I'll just to emphasize what I'm saying here. This is the field. And the atom. And the interaction. Right? I have to calculate the matrix elements of all three terms. So what is this? N times h bar times the cavity frequency. Right? What is the atom part if I take the ground state to be at zero energy? Zero. What is the interaction term? Zero, right? It's zero because neither the sigma plus nor the A's have diagonal elements there, so that's 0, 2. So this is equal to n times h bar omega c. Okay. What is the matrix element? Oops. So again, we're looking at this basis, so I have to look at that guy. I don't want to write out all the terms. You tell me. What is that matrix element equal to? So firstly, the field, right? The field is what? N minus 1 times, right? Because they have N minus 1 photons. The atom, which is the energy of the excited state, we'll call it h bar omega Eg. And what about the off-diagonal element? 0. Okay? So I will rewrite this as N times omega C minus h bar delta, where delta is equal to the cavity frequency minus the resonance frequency. That's like the detuning that we had in the case of a laser, but now in place of the laser frequency, we have the cavity frequency. Okay. Very good. What about an off-diagonal element? We don't have to calculate one of them because the other is just the complex conjugate. So this is equal to, we'll just write it out in this case. Now, wait a minute. There's a horribleness that we're left with in here, which is that G is used twice for two completely different things. You know, you might say, why don't you change notation? I'm sorry. That's just how it is. This is what everyone uses, and usually I decide, I'm going to have the Deutsch way, but not this time. I'm going to do it the way everyone does it, and G just means two different things, and you just have to know what you're talking about. Here, G is equal to, as you remember, you know, this was minus square root of h2 pi h bar omega c E dot E divided into the strength of the field at the position of the atom, right? In units of h bar. That's the coupling constant G, and then we use G to represent the ground state. And I'm sorry, it just means two different things in two different places. Okay? All right. Right. So, let us, with that said, we have h bar G, not to confuse with G, is equal to minus 1 A N E plus now I'm writing out every term. Some of these you can see by eye, and you would never write them like this. But I'll just do it carefully and slowly here for now. Okay? What is this matrix element? Root n, right? Because when I lower it, but I get the root n. And this is 1, right? So this is equal to h bar root n times g. And what is this?
Square root of n plus 1.
Right, but then I got this as 0, right? So I didn't really have to write this term down because it's clear that sigma minus doesn't do anything to that 0. So this matrix element is that, and that's equal to, since this is all real, the other off-diagonal element because it's a Hermitian operator. Okay. All right. So, I learned the secret to erasing the board. Don't use those pens. Use these. Good stuff. These are good. All right. So, let us now write down the matrix. So, H sub with nt is n, written as a matrix in this basis, the basis where I put first this, and the second guy is that. is equal to, I'll factor out the h bar, n omega c minus delta. Oh no, I'm going to write it, yeah, I'm going to write it in this order because I like the excited state as spin up. Order basis. Square root of ng, square root of ng, and omega c. Which is now a new kind of pseudospin. A pseudospin that involves not only the atom, but the photons. This is a two-level system. It's a two-level system that involves both matter and light, right? There are two different states. So I'm going to call this guy spin up, and this guy spin down. Oh my God, but that was spin. But whatever, we just did it. Don't you love this abstraction? So now this is equal to, I can write it, well, there's the identity part. So what I am doing is expressing this in terms of the standard identity and the three Pallies. I can always look at the identity part in terms of the trace of this over 2. And then I take the trace with sigma z over 2, that gives me this. And the trace is with sigma 1, so you can check for yourself, if you write in the Pallies, that that's that matrix. Okay?
You don't need the sigma 1 by 2, right? It's just sigma 1.
It's just sigma 1. You are so right. Thank you, Vickers. Absolutely. And that's important. It's that damn factor 2 in my head. I was trying to get his head, which I can call this, if we like, to make it in comparison to what we had with the laser. Remember, with the laser, we would have the delta over 2 and the Rabi frequency over 2, which means that the Rabi frequency is square root of n times 2g. That's just how it is. I wish we had defined g with the 2 in it, but I didn't make the rules. I'd like to make the rules, as you know, but I don't. I didn't in this case. Right. So, by the way, how do we physically understand why there might be a square root of n in our Rabi frequency that's associated with these n photons? Why is the square root of n? Yes, sir.
The field of the laser?
It's related to the field, right? N is the intensity. It's the square of the amplitude, right? So that's why this is the square root of n. Hopefully that the algebra of A's and A daggers did that, right? Okay. So this is like the electric field strength times dipole of n photons. All right, excellent. So I ask you now, what are the eigenvectors and eigenvalues of this Genies Coming model.
Spin up and spin down.
No, they would be if you were zero. But there's spin up and spin down of some kind of, I mean, I could say that's fair. There's some kind of spin up. But what are they relative? These are what we call the bare states. These are the states of the atom and the field without any interaction. Without any interaction between the atom and the field, the states are product states, right? Then I turn on the interaction and I get new eigenstates. What are those new, well, easier question. What are the eigenvalues of this matrix?
Is that first term plus or minus the square root of that thing's?
Exactly, exactly. So we have for a given n, we have two eigenvalues. The identity term plus or minus h bar over 2, the square root of delta squared. I'll write it like this. This I is equivalently equal to.
Did you drop an H bar on the first term?
I did. Yeah. N times 4g squared plus, no, I have to go over 3g squared. I have to square that. Okay, those are the eigenvalues, right? What are the eigenvectors? There's one associated with the positive eigenvalue, and there's one associated with the negative eigenvalue.
The cosine times spin up
Exactly.
plus
We know that this whole Hamiltonian is something times the identity plus h bar times some effective total thing dotted into sigma. Right? That's what this Hamiltonian is. Where h effective, I mean the effective Rabi frequency here, is equal to minus the detuning in the 3 direction plus omega n in the 1 direction. If I dot this into this, I get that. And so and I write this now as, you know, the square root of h bar. No, I don't have an h bar there. It has a magnitude and a direction. And that direction is given by, has an angle. The direction of this guy is relative to the 3-axis. It has some angle theta. Theta sub n is the arctangent. Right? It's got some direction in this horribly abstract space that we've just created for ourselves. And so this has cosine of theta sub n over 2. Spin up, and spin up here is that, plus sine spin down, which is that. And it has a superposition like that. So, these, my friends, is what we call the dress states. They are now atoms and photons dressed together. Sometimes this is known as a polariton. It's a kind of quasi-particle of the field and atoms together. Sometimes this is known as a atom-photon molecule, in the sense that it's a kind of combined eigenstate of the atom and the photon together. Okay? And these are the dressed energy levels. So let's look at the spectrum. All right. What we're going to write down is what is commonly known as the Genies Coming ladder. Let's begin by taking the special case of resonance. Let's suppose, I'm sorry I crossed that out, I meant to underline it. So let's look at the special case of resonance, where we choose the cavity to be exactly at the resonance frequency of the atoms. Okay? So that delta is 0. So, let's first draw an energy level diagram for the bare states before we added the interaction. So, before we added the interaction, I could have NT is equal to 0, or 1, or 2, etc. So this state was that. I could have one excitation. And there were two energy levels here that, in this case, for the bare states, are degenerate. Right? So this splitting here is the cavity frequency, which is the same as the atom frequency. And then I could have two excitations. These are degenerate in this case. So these are what we call the bare states. And this is the spectrum, right? It's infinite ladder, with this doubly degenerate states when I'm right on resonance. Either I have the energy in the atom or the energy in the cavity, and if I have one excitation, two, etc. Now I turn on the now I'm going to turn on the coupling. What happens to these levels? Well, they split. They split due to the coupling. One goes up by this amount. I mean, here delta is 0, right? One goes up by this amount, and one goes down by that amount. And so the splitting, this becomes two hybridized orbitals don't want to be molecular, make Susie happy. And then I have the state, the plus state and the minus state, right? And the splitting between these guys is equal to, in this case, 2 times h bar times 2g, right? Because 2g is the Rabi frequency. When I have one excitation. What about these guys now? Well, they get split as well, but the splitting is bigger. This is the plus state for n equals 2, and this is the minus state for n equals 2. One goes up by this amount, and one goes down by this amount, right? And so what is the splitting in this case for these hybridized guys? Well, it's h bar times 2 square root of 2. And generally, the splitting would be h bar times 2 square root of n. Square root of n times 2g. Right? So I'll have a different splitting. This is an anharmonic ladder. This is not a linear system because my two-level atom wasn't a harmonic oscillator. If I had the coupling of two harmonic oscillators, then I would have normal modes and the energy levels would be harmonic. The anharmonicity is coming from the fact that I don't have a Lorentz oscillator sitting inside that cavity, a charge on the spring. I have a two-level atom, which has a nonlinear optical response, and that gave me this nonlinearity. Now, if I'm off resonance, we can take just a quick look at that. Let's say I have red detuning, even though I have only a blue pen. But now I have a blue figure. Yes, sir?
Where does this nonlinearity come from?
It comes from the fact that the atom is a saturable absorber. So the atomic response, I mean, one way of looking at it is that, you know, you're pulling the electron away from the nucleus, but in a way, because of the Coulomb force, is a very nonlinear thing. Ultimately, it's because, you know, the whole business of Rabi oscillations is not the classical picture of charges on the spring.
So over there we don't have nonlinearity, but here we have.
We do.
Yeah. So
It's-
because quantum mechanical optics.
I think that's fair to say. I mean, the atomic response, what we saw in Rabi oscillations, is a quantum mechanical response. I think that's a fair description. All right, very good. You know, just as an aside, in the context of the circuit QED, it's a similar kind of thing. There it's the Josephson junction, which has a nonlinear inductance, which makes for this kind of nonlinear response. Yeah.
Do we have to worry about level crossing?
We would, in principle, if we're in what we would call the ultra-strong coupling regime, where the G is on the order of omega c. But this is not to scale. Not to scale. In an optical case, this would be 10 to the 15 hertz, and this would be, you know, I don't know, a megahertz. So these guys never get close to one another. And similarly, even, you know, if I'm you know, if I'm a microwave and I have some gigahertz, you know, this is some megahertz, is 1,000-fold separation here. So these levels never get close to those levels.
So you can, and it's 1,000 photons in your cavity.
Yeah, when you start getting up there, you have to start worrying about some things. But at that point, I mean, we'll come back to that, how I would want to create a 1,000-photon Fock state. No, we never worry about that. Yeah. All right. Red detuning. In that case, my bare states are the following. Let's come back over here. We have this detuning, right? So if I look at this energy level, the ground state is fixed at this energy with this number of photons, and the excited state either gets below or above that, depending upon whether an additional photon has slightly less energy than the atom or slightly more energy. Yeah. For red detuning, there's more energy if the atom, if the excitation is in the atom than in the photon, because the photon has slightly less energy in the two-level system. So in that case, we would see something like this for the diagram. So this is ground state with one, or the excited state with 0. This is the ground state with 2, or the excited state with 1. This is the ground state with 0, and this is the detuning. Okay. That's for red detuning. For blue detuning, it would be switched. This guy would be above, and that guy would be below. And then this guy gets hybridized into these nonlinear thing, where this splitting now is h bar times the square root of 4g squared plus delta squared. And this guy, this splitting is h bar 2 times the 4g squared plus delta squared, etc.
So it's, not to be rude, but it's a little bit misleading the way you draw that diagonal line, because when you get to the hybridized, it contains pieces from both.
That is correct. Yeah, yeah. I mean, this it's particularly in this case, this guy would be an equal on resonance. This would be an equal superposition of those.
Yeah.
Now, when the detuning is big and delta and theta is small, then it's not so wrong to make this, if you notice, although I did this completely by accident, this is a solid line and this is a dotted line. It was sort of true, because when the detuning is very, very big, the dress states are dominantly one or the other, right? If theta is a very, very small number, then this guy is dominantly ground with n, and the other one is dominantly with a small admixture or add superposition of the other guy. And these are the dress states. All right, I'm gonna bring back this. Right. So, you know, in modern experiments, the kind that are done, particularly at the Yale group, they have these three-dimensional, instead of those strip line type transmission lines, they have actual three-dimensional cavities of their, because you can get a much, much stronger, a good resonator in that case. And the questions here that I want to just quickly raise here is, oh, I should have, maybe I'll cheat and use this, be a PowerPoint guy for a second. What if we started the atom, as is shown in this picture, in the excited state, and it transfers through the cavity? All right. What's going to happen to the atom if it's in the excited state at time t equals 0?
It'll be, I mean, it's a linear combination of two.
That's right. And in fact, this state is not an eigenstate of the system, right? So the system will evolve in time. And what it will do, it couples to the only other state it can couple to. The state has one excitation. That excitation could be in the atom, or it could be in the cavity. And this is what's known as vacuum-Rabi oscillations. The system would oscillate, as shown there in that box purple thing, between being excited with no photons in the cavity, or being in the ground state with one photon in the cavity. Then it will reabsorb, re-emit, reabsorb, re-emit. And intermediately, it would be in a superposition of those two. Yeah, Brian, you have a question? No.
So the frequency there is totally independent of like the excited state lifetime? It's
That's a good point. It's an awesome point. And the answer is yes, and let me return to that in just a moment. What determines that frequency of that oscillation is G, the coupling strength. So it will oscillate at what's called the vacuum Rabi frequency. Now, it really should be called the single photon Rabi frequency. It's the Rabi frequency associated with one photon, and that is equal to 2G. That is, if I were to ask what's the probability to find one photon in the cavity, it would oscillate cosinusoidally or sinusoidally with a frequency 2G. Independent, not depending on the cavity lifetime. Matt, you have a question?
So this is assuming that the excited state atom enters the cavity non-asymptotically.
That's right. That's right. Otherwise, it would just dress it. Indeed. But if I shoot it through fast enough and the time spent, I choose the velocity such that the transit time is equal to that, I will exactly deposit one photon in the cavity. And the atom will be in the ground state. That was one of the experiments done at the Orlando group. I want to just say one or two words here about something Brian just mentioned, which is truly important, which is that generally speaking, these excited states have a finite lifetime. Now, for the circular Rydberg atoms, we can forget about that. But for the optically excited kind of cavities and Faraday-Pro cavities, we sure can forget about that. That might be, you know, a few nanoseconds. Moreover, light might either leak out of one of the mirrors or be absorbed by one of the mirrors. So there's a rate of loss of photons. And so the whole business of cavity QED has been about getting into what's called the strong coupling regime, whereby G, the single photon Rabi frequency, is sufficiently big compared to the rates of decay. This atom could spontaneously emit out the side of the cavity. So if I looked at this Faraday-Perot cavity, the atom can emit into the mode, that happens at the rate g, but it could also there's 4 pi steradians which can go in any other direction. And that happens at the spontaneous emission rate relative to the lifetime. So the whole name of the game in cavity QED, and what the famous Jeff Kimball, who developed this, spent his entire career trying to do, is to try to make these cavities better and better and better to ensure you had a really strong coupling regime. And everybody who comes from an atomic physics background is licking their wounds and feeling horrible about the fact that it just works so much better within the solid state. The reason is, the question is, what is the size of the electric dipole? Because D, the G coupling constant here depends on the dipole moment times the field strength. Well, in an atom, if you've got atoms near the first excited state, you know, the dipole is 1 atomic unit. It's a Bohr radius away from the nucleus. You could do a lot better with Rydberg states, which is what Arosh did. But if I look at this chart, which I stole from somebody's talk a few years back, you can kind of see, and this is already old, the size of these things. The size of the dipole moment for the cesium atom, experiments into that, versus the Rydberg atoms, versus the superconducting circuits. The superconducting circuits, you're talking about a macroscopic antenna. It's a big thing, and that's already small compared to what they currently have. It's huge. You can make a huge. Now, of course, the field isn't as big. You're not confining it as much, so your G's aren't that much bigger in the end. But these guys have such long lifetimes. The cavity lifetimes are so much longer than they are in the optical regime that you can get very deep into the strong coupling regime. And things that, when I was a graduate student, I thought were silly to ever even think about doing, when people would write down funny models of quantum optics. You'll never get those lifetimes, that's crazy, is now an everyday affair in circuit QED. And so the Genies Coming model is now the workhorse of the way in which we manipulate quanta in a variety of kind of quantum technology.